Okay, right here I'm going to work examples 3 through 5 from the PowerPoint. What I'll do is over here I'll put the time for each of the 3 through 5, excuse me, at the time at which I start all 3 of those. So if you want to refer to that to skip stuff. I will note that 1 and 2 were in an earlier video, so you can go find those later. Okay, so here we go. So two cars collide in an orthogonal intersection. Orthogonal just means it's a fancy word to say that it is perpendicular or at a right angle. Right angle. Okay, so okay, from a top view of the intersection, the first car is 950 kilograms. Again, a lot of times it's nice to have colors for these sorts of things. I'll go ahead and draw the car as speed and is approaching from the left. So we got a car here. Okay, and it's got a mass of, let's zoom way in, 950 kilograms. Okay, and it is approaching from the left, so that means it is going this way. Okay, 16 meters per second. 16 meters per second. Okay. The second car is 1,300 kilograms at a speed of 21 meters per second, approaching from below. Okay, so let's get some blue, and let's put that on there. So we go get a nice blue car. It's a little bigger than the black car, 1,300 kilograms, and it's going this way. It's going faster, so I guess technically that line should be a little bit larger, but whatever, can't be perfect. They collide and stick together. Find the speed and direction of the vehicles just after the collision. Assume there are no external forces. Okay, so we want to know, where do these guys end up? Okay, so we know that when they stick together, I don't know what color to use for that. My strongest colors are all taken. So maybe we'll use purple for all you LSU people out there. Okay, so anyway, so they stick together. So the key language to this thing is that they stick together, right? So they become like a combined car, right? They collide and stick together. Collide and stick together. Okay, so this car right here or this combined mass here, is really, it's got this 950 on this side. It's got this 1,300 kilograms on this side. We're assuming no pieces flow off. But all told, really, the point of all of this is that all of it told is just one massive car, right? So I could fill all this in, and it's just a big car, right? With a mass of 2,250 kilograms, right? So anyway, and we know, generally speaking, that it's going to fly off this way, okay? Now, the question asks specifically, it says, find the speed and direction. So basically, we want the velocity vector, right? The full velocity vector. So we are looking for this right here. So I'm going to call that, I don't know, well, let's call that VF, right? VF equals what? Right, and let's go ahead and just label these things just so that we have a clean, this will be car 1 over here. So M1 will be 950 kilograms, and V1 initial is that. All right, so then let's see, let's go down here, and this is going to be M2 is 1,300 kilograms, and V2I will be 21, well, we don't really want kilograms now, do we? Let's see if we can't erase that, give ourselves some proper units like meters per second. Okay, really nice to give us units that work. Okay, and then this thing right here, this is M1 plus M2 equals that. And VF, of course, is VF. Okay, so this is a nice problem. This is, this is a two-dimensional, perfectly inelastic. So when they stick together, it means they're perfectly inelastic, which means the equation that we typically start with in this case is usually M1 V1. Let's just do it as vector form first. I plus M, well, and we could keep our colors, right? Why not? Colors are fun. So this is usually how we write this out, right? Now the key here, of course, is that we note that these two objects act like one object at the end here. So we're going to combine these two masses, noting that the velocity, V1F and V2F, are exactly the same. So they can be factored out algebraically. I mean, it's nothing really different than just saying that this all acts like, one object, really, after the collision. Okay, so when we do that, we're left with M1 V1I plus M2 V2I equals, and then I guess we'll do this in purple, M1 plus M2 times, instead of calling it M1F and M2F, we're just going to call it, V1F and V2F, we're just going to call it VF, right? Okay, so that's essentially what happens when we have objects that stick together. Now, so that's just kind of the general rule. What we're going to do here, though, is we want to do this in the X direction and the Y direction. So I'll start with doing the X direction. No particular reason for that. I just feel like it. So we'll get M1, V1, I in the X. Okay, cool. And now we want to add, it looks like my plus signs changed colors. Let's see, so M2, V2I in the X direction. Now we note that V2I is straight up and down, so it doesn't have an X direction. So this particular term right here is going to go away, so we don't have to worry about that, which is awfully nice. Okay, and then we go equals, and then we'll do our purple here over here. So I've got M1 plus M2, and now I've got VF in the X direction. Okay, so note that since I'm looking for VF, I can solve for its components, the X component and then the Y component, and then that way we will have the full vector. Okay, so let's go ahead and do just that. So we'll say VFX equals, so I'm just rearranging here, M1 V1I in the X divided by M1 plus M2. Okay, so this is nice algebraic rearrange, and I think we can solve that relatively easily. So let's see here, VF in the X. Oh, it's nice to keep the picture in view if we can. Equals M1 V1. Okay, so I'll plug in and I'll pause. Okay, so if I plug those terms in, I get 6.7556 meters per second. Okay, so we'll go ahead and box that. That's the X component of our vector. So if I went up on my picture right here, it would look like it's like right there. Right, so we know that's 6.7556. It's 5 repeating. Okay, so let's go ahead and see if we can't do the Y component. I guess we'll just do it over here so that I can see my work, right? And it's essentially the exact same equation. Let's see here. So M1 V1 I in the X. Oh, nope, sorry, we're doing the Y direction, aren't we? Y direction. Okay, so these are the kind of things that we need to think about as we go. Okay, and notice that the this particular velocity vector right here is all in the X direction, so it has no Y component, so that's 0. Okay, so now let's add M2 V2 I in the Y. Luckily, this one is all in the vertical direction, so we don't even need to use any sines or cosines here, which is nice. And then let's see here, so we'll go equals. And then, so then the right-hand side, which we do in purple, is M1 plus M2. And we'll do VF in the Y. So here's our VF in the Y is right here. V final in the Y direction. Okay, so that's what we need to solve for. So I'm going to rearrange this as VF in the Y equals, let's see here, M2 V2 IY divided by, in purple, M1 plus M2. Okay, so again, I'll pause as I plug in. Okay, so I'm getting 12.133 repeating meters per second. Again, we'll box that. Okay, so I can look up here. I've already drawn the triangle up here, but I'm going to go ahead and draw it. I'm going to go ahead and draw it down here. So let's see, we've got 6.7556 meters per second in the X direction. And I always like to draw my X's before my Y's, but I could do it the other way if I wanted to. It doesn't really matter. And this will be 12.133 meters per second. Not very good drawing, right? If we were going to go to scale, this one should be about half as long as that one. So maybe if I do it like that, and then we just zoom in, powers of computers, right? We can do whatever we want. Okay, and that'll tell me that I should get an angle greater than 45, right? Okay, so we add the two, this one and this one, tip to tail, as always. And then our resultant goes from the initial tail to the final tip. Okay, so there's our resultant. Okay, and let's see. So to get this side, we're going to do, this is going to be VF, right? And VF, the magnitude of that is going to be when we do the Pythagorean theorem. So 6.7556 meters per second squared plus 12.133 meters per second squared. Okay, and the angle, theta, is going to be the inverse tangent Okay, as we know, it's the opposite over the adjacent for this angle right here. And so that'll be 12.133 meters per second divided by 6.7556 meters per second. Okay, so if I'll pause while I plug all that stuff in. Okay, so this is what I'm getting out of the calculator. So I would combine those to give myself a vector. And I would say, well, I guess we need to figure out our sig figs before I write those down. So where's my sig figs? Looks like this original problem. Looks like we're going to have 2. Hold on, you can hear Rocky's really going crazy. So anyway, so we're going to have 14 meters per second at an angle of, this is my angle, 61 degrees. Okay, so let's see, it's not coming out very thick for some reason. But anyway, that's a 14 meters per second at 61 degrees. Okay, and that's all. Okay, so that is example number 3. Okay, let's see. We got nice purple colors for you LSU people. All right, so it looks like, oh, so that was a 2D perfectly inelastic collision. Okay, let's go down to this one. Okay, this one is very cool or very interesting because we haven't done one of these yet. But you always want to look for this word elastic. When it says elastic, that means quote unquote perfectly elastic, and that's the only way you're going to know it's elastic. It's going to have to tell you that word right there. I mean, I guess you could end up in a problem where they ask you, is this an elastic collision, and you have to work backwards to see if your equations hold. I won't ask you that particular question, or at least maybe I would ask that for the honors. Anyway, this should just be musing here. But anyway, so 2 bumper cars in an amusement car collide elastically as one approaches the other from the rear. Okay, so we've got some rude person who's going to bump somebody who's not paying attention, right? So this one's going this way. So if they're bumping it from the rear, that means they're both going the same direction. So I'm going to go ahead and draw that like this. Okay, let's see. The car in front, car A, has a mass of 550 kilograms. 550 kilograms. So let's see. The car in front has a mass of 550 kilograms, and the car behind it, car B, has a mass of 450 kilograms. Well, these problems are always easiest when they have the same mass. But I guess in these example problems, I didn't want to do that. It kind of makes sense to me, but anyway. The car in front was traveling at 3.7 meters per second, while the car behind him hit him with a velocity of 4.5 meters per second. Okay, so we got 3.70 meters per second. And right here, we've got 4.50 meters per second. I believe I got those numbers right. Yep, 4.5. What are their final velocities after the collision? Okay, so this elastic thing right here basically gives us our second equation. Okay, the thing about these problems is it seems like they don't give us enough information, but that word elastic creates essentially a second equation for us, a second condition that allows us to solve this. Okay, the first equation, well, first thing, let's note that this is one-dimensional, so we're only going to be working in the x direction. So I'm going to go ahead and define positive x as in this direction. Okay, this is before the collision, before. After the collision, we don't really know what's going to be going on. It seems highly likely, in fact, it seems absolutely certain, that B will be moving slower than that 4.50. It might even bounce back, but somehow I doubt it. So I'm going to call this VB final. Okay, and then VA final. Here's A. A will be moving faster, right? VA final. Okay, now in this case, I think it should be fairly clear that that they're both going to be going off to the right. Maybe it's not 100% clear. Maybe you have a guess that car B is going to go backwards. I would recommend that if you don't know which way they go, you always guess they're going to the right. Sometimes even if you're sure you know which way they're going, it's kind of nice to just if you don't know which way an arrow is going to go, just make it go positive. And that way, when you solve for it, if you get a negative number, you know that negative number just means, oh, I assume the wrong direction is actually going negative. If you assume it goes to the left and you get a negative number, that means it's actually going to the right. And to me, that's just very confusing, so I don't ever really do that, okay? So anyway, so we've got a collision. So anytime you have a collision, the first thing we want to do is we want to do a conservation of momentum. So the momentum beforehand, I'm going to go ahead and write as, let's see, well, I'm going to go kind of in order of the cars, which is a little bit unfortunate, but, you know, so this would be mass of car B. Oh, wait, are they going to the right? Didn't even say. Oh, they didn't even say it was going to the right. Anyway, okay, so so I have, you know, carte blanche to do whatever I want there. So mass of car B times the velocity of car B initial, okay, plus the mass of car A times the velocity of car A initial equals, let's make our operations black, I guess. Okay, so then we're going to look after. So after, we've got this down here. Okay, so the mass of car B times the velocity of B final plus, and blue, man, I really murdered that. You know, plus the mass of car A times the velocity of A final. Okay, cool. So the cool thing about this is, you know, VB initial is known. VA initial is known. We know both the masses. So, in other words, we have two unknowns, VBF and VAF. And those are the two unknowns that we're looking for. So we can solve this. We just need another equation. Okay. Now, your textbook has an equation for an elastic collision. I need to find it. Okay, this is the equation for, according to your textbook, and it's on your equation sheet. Now, it's got these on top. Those are an error. Those should not be there. This is an equation for an elastic 1D collision. It can only be used in an elastic 1D collision. Okay, you cannot use it at any other time. Okay, so we don't need these vector symbols because it only works in one dimension. Okay, so that's a little confusing. The other thing that I find confusing about this, well, first of all, for this particular problem, I wanted to copy it down exactly because I wanted to talk about it a little bit. But I should note that, and this should be fairly clear, is that these ones, we're going to turn those into B's. And then those twos are going to turn into A's, right? Just because for this particular problem, they label them not by numbers, but by letters. The other thing that I will note is that, you know, when I derived this equation in class, I didn't write it out this way, right? I wrote it out in a much, to me, much cleaner way, which was VBI plus VBF equals VAI plus VAF, okay? And I think if you stare at the algebra long enough, you'll see that that's the exact same equation. It just has fewer negative signs, and so I find this one to be a little confusing. However, that is the one that is on your equation sheet. Okay, so you may do this any way that makes most sense to you. Okay, I think I'm going to do it this way because that's what's on your equation sheet. It's really neither here nor there. Okay, it's whatever it is. It's whatever you want to do. Okay, so we're gonna work I guess we're gonna have to work sideways for this to make this. Anyway, so just remember that can only be used for an elastic 1D collision. Okay, I think it would be easier to just use this one that I'm about to erase, but that's up to you. Okay. Okay, let's see here. I don't know why your book decided on this particular version of this particular equation. Okay, so what we want to focus again on is the things that we were solving for. So we're solving for VBF and VAF, right? So both of our finals. Okay, and those are both right over here. Okay, so I need to isolate one of those in order to plug it into that equation up there. So let's go ahead and do that. I'm going to work in black, I think, here, just because switching the colors. I just went back and listened to it, and there's a lot of this sound, maybe too much. Okay, so anyway, so VBI minus VAI. Which one do I want to isolate? I don't know. We're going to have to bring a negative sign over. Equals VBF minus VAF. Okay, I guess we'll isolate VBF. So we're going to have VAF minus, so I'm just going to take that and bring it over here. I'm going to distribute that negative, so VBI plus VAI equals VBF. Okay, cool. So now I've got VBF isolated, so I can plug it back into that top equation. Okay, so the top equation becomes MB VBI plus MA VAI equals, let's see, MB, and now I need a big parentheses so I can plug all this stuff in for VBF, right? So VAF minus VBI plus VAI plus VAI. Okay, now I need my last term, which is going to be plus MA VAF. Okay, and all of a sudden a relatively straightforward problem has gotten what's the word? It got expanded, right? And so we want to be very careful here as we work through this with the subscripts. Okay, there's no guarantee that I won't mess this up. You get better at this the more you do it, but you still make mistakes, right? So we want to focus that the thing that we're solving for in this particular equation is we're looking for VAF. It should be in two locations, here and here. Okay, so we're just going to start, doing some algebra. So MB VBI plus MA VAI equals MB VAF minus MB VBI plus MB VAI, right, plus MA VAF. Okay, so I'm going to try to isolate VAF, so I'm going to take all of this stuff and I'm bring it over to the other side. That will change all of its signs, right? So we'll get MB VBI plus MA VAI plus MB VBI minus MB VAI equals, okay? Now with the two remaining terms over here, I'm going to pull the VAF out, and what is left is an MA and an MB, MA and an MB. So I'm going to divide that on both sides. So I'll get MA plus MB. Okay. Yeah, I think hopefully, if you do that algebra out yourself, it'll make sense, I think. Okay, so now I'm going to plug in because I know all of that stuff. So VAF equals, I'm going to pause while I do that. Okay, I'm getting a very clean 4.42 meters per second. After a kind of lengthy algebraic thing, I recommend plugging this into your calculator 2 times, and double checking all of your subscripts to make sure that you get that right. Okay, so anyway, so we get this, cool. Now we need VA or VBF. How are we on sig figs here? Looks like we're probably okay. I think the initial problem gave us 3 of everything. Let's see here. Yeah, we got 3 here, we got 3 here, we got 3 here, we got 3 here. No weird additions going on here that I think would create a problem, so we're all right. Okay. Okay, so now we need VBF. How do we get VBF? Well, we're going to get it from right here, right? We're just going to plug and chug right in there. Okay, so again, I'll pause as I plug these numbers in, and we'll get the final answer. Okay, so working the algebra out, we get 3.62 meters per second. So in fact, if you have an elastic collision, which, I guess a bumper car might be a pretty close approximation of an elastic collision, just assuming the bumpers are designed to give back as much energy as they receive, or at least as close as humanly possible. You can see that, so afterwards, if we just kind of look at our picture, this one is now going, 4.42 meters per second, and the one in back is going 3.62 meters per second. And that kind of makes sense to me. The back car is going to slow down a little bit, the front car is going to speed up a little bit, okay? And if it's an elastic collision, no energy was lost. Now I do want you to remember that, this is the version that your book uses. This is the version of the equation that your book uses. But a much easier equation is that this one plus this one, okay, all the ones with the A's, equals this one plus this one, right? So, you know, if I add these two, if I add this one plus that one, I can almost do it in my head, right? That was a 8.12 meters per second total, right? And if I look at this one plus this one, and I go right on down here, oh, look at that, it's 8.12 meters per second, right? Okay, so the easier version of this equation is that VA1 I plus VAF equals VBI plus VBF. Okay. And I just highly recommend, I would almost recommend memorizing that. That's going to be way easier than dealing with these negative signs. I think algebra in here is it's hairy, right? It's not that, everybody in this room, well, not everybody in this room, everybody in this room, that's just me and Rocky. Rocky's not good at algebra. So 50% of the people in this particular room can do this. And in the room that you are sitting in, assuming it's a classroom, everybody can do this. But even in this room, not even, none of us are going to get that right every time. It's just fraught with errors. So just be aware. Highly recommend this particular version of that equation. Okay. All right. Okay, moving on. We're going to do this last one. Ooh. Oh, we got an elastic collision. Okay, I think, and look at this. I really need to get in there and fix these subscripts. Anyway, this is emergency COVID stuff, so I will do a better video of this at some future date and delete this one. Okay, calculate the velocities of two objects following an elastic collision. Boom. I think this time I'll use the other equation, given that we got mass 1, mass 2, V1, and V2. This is essentially the exact same thing we had last time, a second ago. So let me just, write down all of my information. Mass 1, mass 2, V1I, V2I. All right, so here we go. Boom, 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 boom. Okay, M1 is a half a kilogram. M2 is 3.50 kilograms. V1I is 4.00 meters per second. And V2 is 0. Sweet. Okay. Now, elastic. So that's good. And, we'll just write that down here. Elastic. Okay, so we don't have to worry about the fact that whether or not these are bumper cars or anything like that in this case. So let's go ahead and solve it. Okay. So in these cases, you've got an elastic problem. So it means we've got two equations, conservation of momentum and conservation of energy. Okay, so the conservation of momentum is going to look like this. M1 V1I plus M2 V, that V got small on me. V2I equals M1 V1F plus M2 V2F. Okay, cool. So that's conservation of momentum. Okay, so it just says the momentum before equals the momentum afterwards. Okay, let's go ahead and clean that one up right off the bat. I know that V2I is 0, so this term is going to go away. Okay, yeah, cool. The unknowns here, as always, we don't know the final velocities of both of these. Okay, now we're going to do energy. Okay, energy. Now, I'm going to use the form of the equation that I prefer, which is going to be V1I plus V1F equals V2I plus V2F. Okay, let's note the things that we're looking for. We're looking for the final velocity. So we're looking for this, and we're looking for that. And we also know that V2I is 0, so we know this one's 0. So that makes this particular case a lot simpler, because this bottom equation right here is already solved for one of our unknowns, right? I mean, I could rewrite it if I wanted to. V2F equals V1I plus V1F, right? So it's solved for one of our unknowns. So I can plug that right in above and get straight to work. And I think I'm going to do that, right? I don't know why I wouldn't do that. It's all ready to go. So let's see here. So I got M1 V1I equals M1, did I solve for V? No, I solved for V2F. So V1F plus M2. So in place of V2F, I'm going to put this expression right here. V1I plus V1F. Okay, so the things that I'm solving for, again, remember where they are. It's right here and right here. So I'm going to isolate that variable as best I can. Okay, so let's see. M1 V1I equals M1 V1F plus M2 V1I plus M2 V1F. Okay, again, let's keep track of what it is that we're trying to isolate. It's these two things right here. So I'm going to take this term and I'm going to bring it over to the other side. And let's see, so it'll be M1 V1I minus M2 V1I equals M1 plus M2. I'm just going to pull that V1F right out, V1F. Okay, I'm going to go ahead and, rewrite over here. I'm just going to copy it down. Okay, and slide up there, V1F. I haven't changed anything, but let's zoom in. Let's go ahead and solve this for V1F. So V1F equals, oh, that's interesting. They've got the same V1I there, don't they? So I'll get M1 minus M2. I'll just pull that V1I out. And I'll divide by this guy, M1 plus M2. And I think we're going to fix that little F right there with an I. I said I, but I wrote F. Okay, cool. So I think at this point, we're ready to plug and chug. So I'm just going to pause it while I do that. And actually, this is nice and clean, because, we've got a 4 on the bottom, and we've got a 4 on top. The 4's cancel. And then I've got a -3. So I'm going to end up with a -3. And of course, my calculator has it come out nice and even. So I need to start thinking about sig figs. And what's interesting here is I kept all the sig figs in this calculation. I'm not really sure why I did. But it turns out it was fortuitous that I did. Because notice we've got 2 decimal places here and 3 decimal places here for a subtraction problem. So we're going to end up with 2 decimal places in our answer. And so that means, right there we've got, -3.0 kilograms. And then, we multiply by something with 3 sig figs. We're still going to stay at we're still going to stay at 2 sig figs. And then we're dividing by something that has 2 sig figs. So we're going to have 2 sig figs in this final answer, which is really obnoxious. But there it is, so there's our V1F. All right, so now we need to find our other solution. This, of course, is the answer with the correct sig figs, but no matter how sig figs we add to it, it's not going to change our computation, right? So, I could add a million zeros on there, and it's, not going to change our computation. So I'm going to go over here, and I'm going to go, okay, well, let's see here. We got V2F equals, well, V1I was 4.00 meters per second, plus V1F, which was, that's what we solved for, I believe. Yes, -3.0, -3.0 meters per second. So again, one decimal place, 2 decimal places, we're going to end up with 1 decimal place here, which is going to be 1.0 meters per second. Okay, and so there's our answer between those two. Okay, so again, this is 1D elastic collision. They're a little gross. But it's not too bad. I really prefer this version of this equation. Okay, I hope that was helpful, and hope you guys are feeling better than I am. I'm probably at 95%. It would be an interesting thing to compare the video I made yesterday to this video, see how I sound. But I do feel better than I did yesterday, and I didn't feel that terrible yesterday. So I should see you guys on Friday. All right, hope all's well. All right, bye.